Now let's turn our attention to example 3, and this is going to parallel very similarly to, I believe, what example 3 was in the last section. That is, we're going to say, what if I was trying to compute this flux integral here, a special surface integral? And if sigma is an oriented surface with an upward orientation, and we're dealing with a curve, or sorry, a surface, z equals g of x comma y, that is, I'm dealing specifically with a function. I'm starting with a function. Then, if I have a vector function here for my vector field of f given by, I don't know, just any sort of formulas in place of the x, the y, and the z component. But if I have this, can I go ahead and actually compute this flux? And will it actually be any easier? Can I find a shortcut way to approach this since I'm starting with a given function? The only way we currently know how to do this is if I start by finding a parameterization. So I'm going to go ahead and see if there's a way that I might be able to get around this. So let's see. First, I'll deal with this idea of an upward orientation. So I'll say that we know that the orientation of sigma is given by n equaling, and I think it can equal this, square root of a g partialed with respect to x of x comma y all squared plus a g partialed with respect to y of x comma y all squared plus 1 multiplied by, a negative gx negative g partial with respect to y comma 1. Now, if you have no idea where I'm pulling this from, I'd ask you to go back and take a look several pages back in the notes, because we actually saw this from earlier. If I go all the way back near the beginning, I might see that up here we established that there were two possible orientations for any orientable surface. One of those orientations would be given by n, and the other would be given by negative n. What we've been using in the past several examples is that if I had a parameterization for my surface, then this would represent my n. And then remember that we had some issues where, if I scroll back down here, where in my simplification, my n and my ds simplified down and I arrived at this integral. Well, what we can also see is that we have another way to calculate n. And we saw this again back in section 5.5. You could go back there and watch some of the videos to see where this happened. But we also saw that this would serve as a vector that was normal to the surface. And so a unit normal vector would just be this vector multiplied by or divided by its magnitude. And in fact, I know that this is going to be dealing with a upward orientation because, again, this z component here is positive, indicating that this vector is tilted upward. So when I scroll all the way back down to the question we were looking at, we can say that this definitely represents, again, an upward orientation, because, again, my upward orientation is signified by this positive z coordinate that I have there. So if I have this, then when I want to go ahead and actually compute my f dot ds, remember this was just an alternative way of expressing what we had said was f dot n ds. If I was to go ahead and rewrite this one final time, I can see that what I'm going to end up with here is my f, but ultimately dotted with, and I'm going to have to put in my n, which is going to be this negative gx x comma y, gy x comma y, comma 1, divided by my radical. I'm going to do my best to squeeze this in here. And then I would still have to replace this ds. But again, ds has a very easy replacement that we also saw in the last section. It's going to be my square root gxy squared plus gy xy squared plus 1 dA. And so what we can actually see here is that if I'm starting with a function as opposed to a parameterization of the surface, I still get a nice simplification here. And what I can actually do then is to simplify this down to just look like a double integral over d of my f dotted with this vector here, which again operates as a normal vector to the surface with an upward tilt. So I have this. If I was to go ahead then and actually think about some other ways I could potentially work with this or rewrite this, I can notice that this vector that I have right here actually kind of resembles a gradient. Notice that the first component is a derivative partial with respect to x, the second's a partial with respect to y, and the last could be thought of as a partial with respect to z. So I'll say, notice that if I had a function, let's call it capital G, and it was equal to z minus, oops, not f, but z minus g of x comma y, then the gradient of g is exactly equal to what we have listed up above. And so if that's the case, then I can go ahead and actually say that if I had my f dot n ds, I can think about fully simplifying that down into an f dotted with a gradient of g, where g is defined as taking my z and just subtracting over my g formula. When I take its gradient, I generate this vector, and the dot product of those will actually generate exactly what I need. So notice what we're establishing here in example 3, and this is very crucial. It's so important to save you time and frustration, is that if I'm starting with a function, I can actually, instead of going to a parameterization, I can just kind of define this g function and then go ahead and take its gradient and do f dot the gradient of g and end up with exactly what I'm shooting for. In fact, we summarize this in the formula below. If f is some vector field, it's a continuous vector field defined on an oriented surface sigma with upward orientation, notice here again with upward orientation, then it's the case that the flux across sigma is given by, just like what we said above, I can do f dotted with my gradient of g, take that, dA. So this is really, really powerful. Notice though, if I wanted to change this to have a downward orientation, I would have to replace my g with negative g. Notice I have to take this vector up here and multiply it by -1 so that my last component turns into a -1 and has a downward tilt. So this is actually a very similar sort of thing that we did in the last section. We saw that there were two ways to approach a surface integral. We could tackle it by defining our surface parametrically, and we did that again in this section. But we could also tackle it by understanding what happens if we were given a starting function. And if we were giving a starting function, there was an easier way to start to think about how I could ultimately compute a surface integral, or in this case, a flux integral. In fact, if we take a look at example 4 in the next video, we'll see that we can actually revisit what we did in example 2, but try it with this new approach.